In this video, I'd like to work through an example, and in this series of videos, work through a number of examples so you can see the simplification process. So let's begin with our algebraic statement. This is what it looks like. It's quite complicated. And we have a not here, and we have a not here, and a bracket here. Typically, that bracket there corresponds to that bracket. So we have quite a complex algebraic statement, and what we really need to do is simplify it. So how do you go about it? Well, the very first step I would suggest is you remove these brackets, but you do them using the BODMAS sequence. What you need to do is start with this one here, resolve this one here, and then multiply all through by C. Now, once you get it into that stage, you get it into form which is easier to manipulate and spot the patterns to apply further rules. So let's first of all try to simplify it. So we start with this bracket in here. We multiply this block by each of these terms one at a time. So let's do that. Let's use a different colour so you can see this. So we've got A, B, not B, C. That's this first one, plus A, not B, B, D, which is this bit multiplied by that bit. Put our big bracket back on, C, and then we add in A, and not B. Okay, so that's the first thing. We have multiplied out this bracket, inner bracket here. We now have an outer bracket, but before we do the outer bracket, it's worth spotting a pattern straight away. The very first pattern is if a gate is multiplied by its not, right? So the rule is if there's a gate and it's multiplied by its not, that according to the rule, that actually cancels to 0, which means that this term here can be cancelled out. So straight away, we've ended up with a very, very quick simplification. So we'll have the C still, the bracket, A, B, not B, C. This middle term has gone, and we add A, and not B. Okay, so that's where we've got to. Now, when we get to this particular point, what we're trying to look at now are patterns to proceed. Actually, before we go any further, before we do that, we've still got a bracket to get rid of. So let's do that. Let's open up that bracket. So it's C, let's write it differently. Bear with me a second. Let's get rid of that C there, and let's try that again. Right, so we've got A, B, not B, C, C, which is this, right, in that term, plus not A, not B, C. Straight away, we can see another rule here. C, C multiplied together always collapses to one of them. And that comes from this rule, that if x is multiplied by x, it gives you x. So this nicely simplifies, which we will do on the next page. The last statement simplifies to A, B, C, which is the CC collapsed into one, not A, not B, and C. Now, how do we approach this when we get it to this? This is what we call the SOP form, the sum of products form. It's a very important stage when you are going through Boolean algebra. It's at this point that we could go off and use Carnot maps, or we carry on with Boolean algebra. So these initial steps that we talked about are the initial steps for both Carnot maps, badly written, and Boolean algebra. So we've got this. We are interested in the Boolean algebra approach, so that's what we'll do on the next slide. We had A, not B, C, plus not A, not B, and C. So how do we proceed? Well, now what we try to do is once you get it into this form, you start looking at patterns which are similar combinations on both parts or several parts. There may be other elements. Notice here there's a not B, there's a not B. Okay, so there's a similarity there. There's also a C and a C. Ah, that's interesting. So why don't we factorize? And factorization is often a very simple procedure. So we arrive at the SOP form, but we try to factorize it. But we factorize it because we see that and that is common to both. So we get not B, C. Over here we have A plus, and here we have not A. Okay, so that's interesting. Now there is a nice rule which states that if there's a gate and it's ORed with the not of its gate, it always outputs 1. So this structure collapses into a 1, leaving not B, C. Or, finally, let's put it in white, not B, C. And that is the optimized version of the circuit. And how do we know? Because there's nowhere further to go. We reduced it to the fewest number of inputs that are relevant to this. And what's interesting is that A seems to have completely vanished. So what it suggests is, looking at the original circuit, the A input plays no real part in the output of the system.